This screencast is the third in a series on energy systems. This will be focusing primarily on the anaerobic glycolysis energy system. So just reading through the first slide. This system uses stored glycogen, refined carbohydrates, and converts it to glucose. With the aid of enzymes, now the enzymes that do aid it are called glycotic or glycolytic. We'll go with glycotic. With the aid of glycotic enzymes, the glucose is worked upon, meaning broken down. So it's broken down, producing firstly pyruvic acid, and then that becomes lactic. During this process, enough energy is released to resynthesize 2 to 3 ATP. So if we look at it as a concept of here's glucose, Glucose, and we have our glycotic enzymes. Now these glycotic enzymes work on breaking down the glucose. So now here we've got glucose all broken up, and as a result of the bonds between the glucose breaking, we get releases of energy. This energy here is used to resynthesize 2 to 3 ATP, which can then be used for muscular contraction. Now, we end up having, as a byproduct, pyruvic acid. Pyruvic acid would normally enter the aerobic energy system and is then further broken down to release more energy to resynthesize ATP. However, because of the required rate of energy production being very high, hence why we're using the anaerobic glycolysis energy system, the body will use the energy system that allows for the greatest rate of energy production to try and meet that demand. So the pyruvic acid will not enter the aerobic system because that system is too slow. So it sits there. As it sits there, it becomes lactic acid, which is lactate and hydrogen ions. And we know that it's the hydrogen ions that are the fatigue-causing byproduct. When we look at percent max heart rate to try and determine predominant energy systems, here we're looking at the anaerobic glycolysis system being predominant when we're working at 85 to 92% max heart rate. The system will reach its peak power at around about 15 seconds. Could be as early as 5 seconds, just depending on the intensity of the work that is being done. And again, could last at its peak for the activity up until about 25 seconds, again, depending on the intensity of the activity. It will be the predominant system in high intense activity. So if we're looking at high intense activity, the anaerobic glycolysis system will be predominant from approximately 7 through to 30 seconds. That's when it's predominant. At 7 seconds, it will still be increasing its rate of its rate of production, and at 30 seconds, or just before the 30 seconds, it will be decreasing its rate of production. However, for both of those circumstances, it will still be providing more energy than the other two systems. So another way of looking at it, here we have our chain of glucose. The glucose is broken down, and remember this is with glycolytic enzymes. Energy is released to resynthesize 2 to 3 ATP. Pyruvic acid is a byproduct, and because the required rate of energy production is too high for it to enter the aerobic system, it becomes lactate and hydrogen ions, which we term together as lactic acid. Again, from a different text, here we've got glycogen converted to glucose, worked on again by glycolytic enzymes. In this bit here, energy is released so that the process of resynthesizing ATP can occur. So it's joining the adenosine diphosphate and the inorganic phosphate. That's the process which is happening in here to create ATP so that energy can be used for muscular contraction. But as the result of the breakdown of glucose, pyruvic acid, and then because it doesn't enter the aerobic energy system because the required rate is so high, it will become lactate plus our hydrogen ions. So notice here it's got lactic acid and hydrogen ions. If we get rid of the lactic acid and write lactate, so lactate and hydrogen ions. So having a bit of a look at what is happening within the muscle. This is before a 25-second max effort. So we've got lots of stored ATP. We have creatine phosphate, we have glucose, we have lactic acid, so the lactate and hydrogen ions. And in here, we've got our mitochondria. So that's at the beginning. So we have resting levels. At the completion, we have no ATP, so it's been depleted. We have no stored CP. So they've all been split into adenosine diphosphate and our inorganic phosphate, and our creatine and the phosphate have split also. As a result of that, we have increased levels of inorganic phosphate, of creatine on its own. We have more lactic acid than previous, and we also have hydrogen ions in here. And again, although understanding that lactic acid is lactate plus hydrogen ions, I've identified that hydrogen ions with the H+. We have decreased levels of glucose. Why is that? Well, because glucose is used in the anaerobic glycolysis system. Although we're primarily looking at the anaerobic glycolysis system, in a 25-second max effort, the aerobic system will be beginning to make quite a sizable contribution. So it's important to recognise that within that time frame, we're getting more oxygen attached to our hemoglobin being delivered, myoglobin taking that oxygen from the blood and delivering it to our mitochondria, glucose entering also here for aerobic energy production to occur. One of the important concepts for us to understand with respect to the anaerobic glycolysis system is our LIP. Our LIP stands for lactate inflection point. This information in the next few slides comes from the VICA website, and it's the student information on LIP. So a few important things with respect to our LIP. The contribution of that should be anaerobic glycolysis system to energy production cannot be accurately measured blood lactate concentration. That is because at high intense activities where we can't clear or oxidize the the lactic acid and hydrogen ions in our muscles quickly enough, we get a massive buildup in our muscles. So the blood lactate won't then actually mirror the intensity of work. LIP is believed to represent the balance between lactic acid production and lactic acid removal. So it is the balance between, or we could say that production, now obviously talking of lactic acid production, equals lactic acid removal. Once we go past that balance point, where we cannot remove as much as being produced, that's when we get our most rapid increase in blood lactate. Now, although for each individual that point will differ, it's said to range from approximately 1 millimole up to 4 millimole. So it should be within that range. Once we pass our LIP, that's when we start to fatigue as a result of the buildup of hydrogen ions. Now, this increase in hydrogen ions decreases muscle contractility. How does it do that? Muscle contractility means we're looking at decrease of force and a decrease in speed of muscular contraction. An increase in hydrogen ions leads to an increase in acidity, or you might see it as a decrease in pH. This increase in acidity leads to a decrease in glycolytic enzyme activity. So if the activity of the glycolytic enzymes decreases, it means that we are unable to break glucose down as effectively, therefore slowing the rate of energy production from, or resynthesis from, the anaerobic glycolysis system. If the rate of energy production decreases, then our intensity or the output will also decrease. At exercise intensities above the LIP, blood lactic acid concentration increases. The greater the exercise intensity above the LIP, the more quickly we fatigue. Requires complex testing to estimate an athlete's LIP. So this is not a type of test that we would give in the field and to non-elite athletes. So it would be conducted by someone who is specifically trained in the use of lactate testing. It costs a lot of money, requires specialised equipment, and will be done with one person at a time. 7. The greater exercise intensity at which an athlete's lip occurs, the longer they can perform at speed or produce power. So if we've got two athletes, so this is intensity, blood lactate. If we have athlete 1, and here is athlete 2, athlete 2 can work at a much higher intensity before fatigue will occur. So for athlete 1, fatigue would occur at this point. That means that this athlete can work, I said, at a much higher intensity before fatigue occurs. So if you're looking at a 400-metre runner, this runner may pass their lip at the 250-metre mark, so start to slow down, whereas athlete 2 may not be until the 350-metre mark. So they're able to work at a higher intensity for an extra 100 metres, therefore their time will be faster. Now when VO2 max, and VO2 max is the maximum amount of oxygen that can be used by the muscles in a minute to produce energy. So when the VO2 max is the same between athletes, a lip test is a more accurate measure of predicted performance because of what we've just described over here. Lip tests may prove useful in determining training intensities required to improve endurance performance. Looking at recovery, lactate and hydrogen ions can be broken down and removed. They can be oxidized. Using an active recovery, 50% 15 minutes, 100% in approximately 30 minutes. Passive recovery, 50% 30 minutes, 100% 60 minutes. So we do prefer an active recovery so that we can maintain a slightly higher heart rate, we can deliver more oxygen to the working muscles so that we can then oxidize the lactate and hydrogen ions more effectively. So when we look at this with respect to EPOC, this is the second part of EPOC. It is the slow part of EPOC. So that's where we break down and remove lactate and hydrogen ions. And just as a very quick review, the first part, which is the fast part of EPOC, is the replenishment or resynthesis of ATP and CP stores.